So I'm sorry. Welcome to this session. Today we are celebrating International Day of Mathematics. In fact, this day has a relevance to a very special number of in mathematics, pi, which is 3.14, and the day has relevance because this is third month of the year and 14th day of the month. So it has relevance to 3.14. Earlier, this day was celebrated as Pi Day, but since 2020, on the initiative of UNESCO, worldwide now this day is celebrated as International Day of Mathematics. The idea is to showcase the importance of the mathematics and the relevance of the mathematics. And as it appears from the theme of this year's International Day of Mathematics, which has been declared, the theme is the mathematics for everyone. So I welcome to this session on today we are organizing this special lecture by Dr. Dilip Kumar. So on the behalf of the Department of Mathematics and Computer Science of Bhau Banarsi University, I extend a very warm welcome to Dr. Dilip. And Dr. Dilip, I'm very thankful to you for accepting our invitation. Dr. Dilip is working at Department of Mathematics, University of Kerala. He is PhD from Center for Mathematical Sciences and has a specialization in a number of fields like spatial functions, fractional calculus, many topics in astrophysics, and he has published a good number of papers in very reputed journals worldwide, and he has many achievements. He has been honored with the Young Scientist Award for his research by Indian Science Congress, as well as Academy of Physical Sciences. He is the recipient of A.K. Agrawal Prize for Best Publication, and he has also received many Best Paper award in different conferences. And he has international collaborations and a very active research worker. And Dr. Dilip, I once again welcome you to this session and express my sincere gratitude for accepting our invitation. I'm sure that your talk will be very inspiring for the young students and also the people who are not directly in mathematics but a user of mathematics. So I'll not take much of your time, and only request everyone to keep yourself in mute mode. So Dr. Dilip, please.
Thank you, Professor Ahmad sir, for your kind words of introduction. And thank you very much for the patient listeners who have been waiting for almost 20 minutes. Sorry for the technical problem encountered. Anyhow, without wasting time, I will be giving a brief lecture on mathematics for everyone. As Professor Ahmad told that this was the theme of this year's International Day of Mathematics, and this theme was actually proposed by Marco Zarco Sotero from a national high school in Philippines. And this International Day of Mathematics was actually announced by UNESCO in their 40th session general conference in 2019, and the first celebration was held in March 14, 2020. And so that is why we are celebrating this day as the International Mathematics Day. Before that, we used to celebrate this as the Pi Day. In fact, this is the the importance of the day was already explained by Professor Ahmad, and this day is having many other importance also. Uh, but whenever I usually start a talk, I used to remember a great mathematician of our country, Dr. Srinivasa Ramanujan. It is not because of the contributions that he has made, but also because of his uh, quote. And sometimes he may have said this: an equation for me has no meaning unless it expresses a thought of God. I think this is more relevant to the title mathematics for everyone, because suppose whenever I used to do my research work, these words always inspired me a lot, because an equation, whenever we want to find an equation, or we are going to do some research work, it should have something to do with the society, or it should be useful to the society. In that way, it expresses a thought of. So that is why always these words has been inspiring for me. And of course, today we also celebrate the birthday of our great scientist, Albert Einstein. He was also born on 14th March 1879. And I know that most of the people may be knowing who is he, and I don't want to say much about him, but uh, his main theory, still standing theory of general theory of relativity, as you all know, is a much prominent theory, and it has been not been proved, or it has not been disproved till now. So moving further, I am just going into my talk on mathematics for everyone. As the title suggests, uh, in today's talk, what I am planning is to give a brief idea where this mathematics is being used, or I will also illustrate where this mathematical modeling in real life situations, or especially in astrophysics, I can explain that also. And if time permits, I will be moving to various types of models which are being used by researchers, or which are being applied in various areas. Okay. So this was my brief objective of today's talk. As I told, this mathematics is used by everyone, but today, since many of the people who are not belonging to mathematics community, or they are not directly involved with the mathematics, I'm just focusing on them also. So I will reduce the technical terms as much as possible, and if sometimes we cannot reduce the technical terms, I will be including that also. So if anybody have any doubts, you can ask in between or at the end of my session. So we are all encountering mathematics in our day-to-day activities, whether it is measuring. So the thing when mathematics comes into our mind is the time when we measure, something. Suppose you are measuring a land area, or we used to say that this much area is our land, or this much is the area of our house. We directly or indirectly involve mathematics. Most of the people think that mathematics is not directly involved with their daily activities, but it is they are not aware of what mathematics is being used in their specific time, or each and every aspect of our life is actually involved in mathematics. So I am just trying to explore what are the places where we are encountering mathematics. Okay, so even if you move further, even if you walk through roads, you could see several shops is saying discount, summer sale discount is there, or there are 5%, and you can see the mathematical table containing the nutrition content. If you buy a food product, you could see a nutrition content in that bottle. In every places, we have to use in some way or other way, we have to use the some kind of mathematics in it. Now, if you take the sports activities, there also we are encountering mathematics. Suppose you are thinking about the cricket, there is some run rate, the total run rate, or how much runs are required to win the match. All these things involve mathematics. moving further, if you come across the day-to-day activities in our life, we could see that the most prominent theory in mathematics which is applied is calculus. I hope maybe it is not directly involved with our activities, but in some way or other, the calculus is much prominently involved in our day-to-day activities. Calculus is a branch of mathematics which actually deals with motion and change, and it is it's calculus. The word calculus came from a Latin word meaning pebbles, and I hope many of you may be knowing that these two are the concepts. The main concept which deals in calculus are the differential and integral calculus. Now, what is how this differential and integral calculus is involved in our day-to-day activities? See, differential calculus is simply a rise and run game. How? Suppose a person is walking through a road whose equation is known to him. Suppose a person is knowing the equation of a road, then he could, without walking through the road, he can be able to say whether the road goes to the right side or left side, or even the road is uphill or downhill. That he can say, or whether he is walking through a plain road. It is possible if he knows differential calculus very well. See why? Because it is simply the rate of change of an independent dependent variable with respect to an independent variable. Suppose you take the y as a dependent variable and x as an independent variable, then clearly this the rate of change, this differential, the derivative, which we call it as derivative, is nothing but the limit of the change in the dependent dependent variable with respect to the change in the independent variable. So in this way, you could see whether how you could see how this differential calculus is involved in our activities. Even if suppose you take the case of a production destruction model, suppose you are having a model in such a way that there is a rate of change in the production with respect to time, then you have to automatically a differential is involved in that particular situation. So suppose you are thinking about a growth model. Suppose you are considering a production situation. Suppose a businessman is starting his production, and he is changing the commodities. He is varying the commodities, and as per the variation, he will get different results. And how he can, actually he can control the production and destruction by production using this derivative. He can reduce the independent quantities like labor or raw materials. He can control that, and depending upon these materials, he can govern the actual output, that is the production, the product output, the product. So that can be termed as dy by, if y is the output, and then the raw materials are the inputs, then dy by dt will account to the total the rate of change in production depending upon each raw material. So in that way also differential calculus is involved. So this is nothing but simply a rise and run game. How it is a rise? Because when we take the two variables with one variable fixed, and you take a nearby variable and you take the difference, and when you gradually change the difference, and when you divide it by the resulting quantity in the x direction, you are getting a derivative. Actually, when you take the limit, you are actually getting the rate of change of this y variable with the rate of change of this x variable. That is how differential calculus is involved in our day-to-day activities. Now, the another important aspect which is involved is the integral calculus. What is integral calculus? It is simply a slicing game. How? That is because suppose you want to find the area of a mountain region, or suppose you want to find the area of a curved region like this. What you are going to do is you simply slice it. Now, in earlier times, they used to measure the curved regions like rectangles, as they already know the area of rectangles. They tried to make it in the form of rectangles. So in that way, when you slice this curved region in the form of different rectangles, and you find the upper rectangles and lower rectangles, and you take the difference between the sum of the upper rectangles and the lower rectangles, you are actually ending up with the area of this particular region. So the same thing can be used for finding the volume also. How much volume is contained in, how much volume is there present in a curved region like this. Suppose there is in a machinery, in a business, industrial, in an industry, there is a machinery or shape of a cone. What they are going to do is they simply measure the conical area with the product which they are putting inside. And by using the area of that particular region, they can identify how much product is going to be produced. So this can be done by using the techniques of integral calculus. So these two are the strong techniques which are directly or involved, indirectly involved in our day-to-day activities. Now, moving and the two main theories behind this is one is the Riemann approach to integration. That is what we are doing here. That is by slicing, and the other one is the Lebesgue way of integration. That is what we have been studying in the school levels. Now, moving further, suppose if you look at the nature, how mathematics is involved in the nature, you could see different types of patterns involved in our natural resources. Like suppose you observe a sunflower, you could see various patterns emerging in the central part of this sunflower head. You could see different nice patterns evolving. These patterns can be seen everywhere in many of the plants. We can see this type of patterns. It can be in a cactus plant, you could see the same type of patterns, or it can be in a pineapple seed, you could see these kinds of patterns emerging here, or even a coconut crown, you could see leaves are arranged in such a way that this is arranged in the form of some patterns. So what is the pattern behind this? There are so many other images also. I can show these images. Suppose you are thinking about the ocean spirals. You could see different types of spirals occurring in this ocean currents, or you could see these patterns in pine seeds, or you could see that in cauliflowers or cactus or different ferns or leeches. You could see the same type of different kinds of patterns emerging. These are all patterns which are emerging in nature. Or the shelf, there are also still patterns are emerging from the center, or in the space or ocean currents, you could see this, or the ferns. In different natural resources, we could see all these patterns emerging. What is actually the patterns? What is actually the patterns? We usually we are fooled thinking that these patterns are coming from the outside to the interior part of this flower. So that is what we think, but it is nothing but the these patterns are emerging as the number of heads, number of buds emerging out of it. This is nothing but the Fibonacci sequence. I hope many of you may be knowing what is a Fibonacci sequence. It is a sequence which is obtained by adding two numbers, previous numbers, for the next number. That is the fn minus 2 is fn minus 1 plus fn. So that is what we call in mathematics, but it is by simply adding the previous two numbers to get the new number. That is what we call a Fibonacci sequence. And all these patterns are basically emerged from these kinds of budding formations. Now, how? Now, if you closely watch this coconut crown, you could see that this is a more stable tree. As we in Kerala, we used to call it as Kalpavriksha, and it is more stable. How we call it as why we call it as this Kalpavriksha, or why we call it as more stable? It is because of the arrangement of the leaves in it. Actually, the leaves are arranged in this coconut crown in an angle called golden angle. That is, this, if suppose one angle is one leaf is coming at a point, the other leaf will be coming exactly 137.5 degree away from this, the first leaf. If suppose the leaves are arranged in such a way, and a healthy coconut tree will be contain maximum 54 leaves. So if you can see a healthy coconut tree, it will maximum contain 54 leaves. That is, and the 54th leaf will be coming exactly at the same position where the first leaf is there. So the tree will drop that leaf, and maximum we can have 54 leaves in a coconut crown. And the angle which I have mentioned here is what we call the golden angle. That is actually the angle related to the golden ratio, which you are all familiar with. We will come into the golden ratio later after a little part of my talk. Anyhow, in nature, we could see mainly two types of spirals. Actually, one type of spiral, that is what we call logarithmic spiral. And these spirals actually emerging from the outside to interior is actually from the center. Is actually emerging from the center. That is what I can show here. This is the equation for a logarithmic spiral. And as you take it as A as a constant, as you vary A, the length of the distance between the spirals will increase. And if you approximate this, this is what we see is the Archimedean spiral. That is, here it is equidistant from the origin. The spirals are coming equidistant from the origin. And here, if you arrange the buds in this logarithmic spiral way, you could end up with the form which we see in the sunflower head. So that how this is how the sunflower head is being formed. So this is the way the Fibonacci sequence are arranged. Okay, now so this is the equation for the logarithmic spiral. And now here is the Archimedean spiral. So as you reduce, as you keep B as a constant and you take R equal to B theta, you are ending up with an Archimedean spiral. So that is why in these two ways, logarithmic and Archimedean spirals are the spirals which is governed in the nature. So suppose you could see that in some ferns like structure, you could see the logarithmic or Archimedean spiral structures. And in some places like shells, all these things, you could see logarithmic spiral structures. So these are the two prominent structures which we see in nature. Now, moving further, see, this is a artificially constructed, or that we are constructed this by the same structure, that is by filling the Archimedean spiral with diamonds. If you arrange the Archimedean spirals with diamonds instead of circles, you could end up with this type of an image. And what I am saying here is from a paper by Mathai and Davis in 1965, which was appeared in Journal of Mathematical Bioscience. And if you refer to that paper, you will get more details on this. Anyhow, moving further, you could see several types of symbols in our day-to-day activities. These are all symbols, familiar, known symbols to you, because these are all the emblems of the famous car companies. And you could see how this symmetry is involved in these type of patterns. So if you want to study symmetry of these type of patterns, or if you want to study the behavior of these type of symmetrical patterns, you have to learn abstract algebra. Abstract algebra is exclusively designed for learning the symmetry or symmetry of objects. There are many other applications of abstract algebra if you think about in computer science, in cryptology, or in for computer various tasks in machine learning. All these we are using the theories of abstract algebra. Just a minute. Sorry for the trouble. So in this way, we can have various areas where this abstract algebra is involved. What are the other applications of mathematics? Suppose if you take differential equations and Fourier analysis. Suppose in most places you may be thinking about a fan is most probably a fan is being rotating in your room. That is actually involving a techniques of differential equations or Fourier analysis. You could see that a linear or a line is being modeled to move it in a circular direction. How a piston is moving in such a way that it is actually governing the circular motion. That is what we deal in Fourier analysis, and many other applications where this differential equations is being involved. Whenever there is a rate of change is involved, we are encountering with the differential equations. Where are these differential equations mainly used? Most of the physical and engineering theories are based on these differential equations. Sound waves, wave theory are being wave equations or heat equations is being governed by partial differential equations or growth models. As I told, I will be explaining models, different types of models in my talk. Various types of material objects are the rate of change of the properties of the material is with respect to the time or with respect to a reaction taking place in them is governed by differential equations. Electromagnetism or the detection of the radar or the normal conditions, change in the normal conditions, how the radar detects and a threat in the community. It is by using the change in the normal condition. If there is a change in the normal condition with some external activities, there will be a change, and suddenly we can plot a trajectory. When you talk about trajectory, you could see that in rocket launching we usually use the trajectory analysis. All these things are basically or directly or indirectly involved with this differential equations. Or even if control theory or non-linear dynamics and many areas, nuclear physics, all these areas we are encountering differential equations. Now, there are many other, I cannot name each and every applications of the subject, but I can name a few. If you think about computational differential geometry, there are so many things which the complex designs, the vehicle designs, all these being done by various types of differential geometry. That is by computer-aided designs of the machine parts or assemblies or terrain modeling. All these are involved involving the branch called differential geometry. Now, if you move further, there are statistics and probability itself. It is a different branch which has to be studied in detail, where so many applications are there. In our day-to-day life, we are encountering risk. So whenever a risk is coming, there is an insurance will also come. So how the insurance policies are being developed? That is by using the techniques in statistics and probability. So by using the techniques of probability, we usually go to the risk analysis or insurance section, or which we normally call it as actuarial science. So analysis of statistical data or reliability or speech recognition or signal processing or image processing. But in all these places, we are dealing with the data. So whenever you are dealing with the data, we require a model or we require a statistical analysis of that data. So in that case, statistics is involved. So there is no place where statistical data analysis is not involved. So many other places, suppose in aircraft survivability, color, sample acceptance or reliability analysis, all these involve statistics. Now, those places where we are not directly, we cannot directly evaluate. In that situations, we have to think about numerical analysis. Suppose you cannot directly integrate a function, or suppose you cannot directly evaluate the value of a function. In that situations, we usually go for numerical analysis. And physicists usually only need to know about the behavior of this behavior. Suppose they are doing an experiment, they only need the behavior of a function. In that case, normal or analytical method may not be helpful for doing that such type of analysis. So in that time, they go for numerical analysis to identify uh, the behavior of that such situation. So in that case, numerical analysis is estimation of ocean currents or modeling combustion flow or airflow patterns or trajectory formation or description of the paths or scientific programming or modeling or even various types of problems we usually encounter with numerical analysis. Now, other applications are in operation research, optimization, etc. So I'm not just don't want to waste time on this because there are so many other things which I would like to explain to you. So there are so many applications for operation research, or even if you don't think about in a technical side or technical point of view, if you are not thinking about mathematics, there is another side of mathematics that we call actuarial mathematics, or other side is the aesthetic mathematics. When you think about aesthetic mathematics, you could see different types of patterns or different types of number patterns emerging. That is one of the prominent area emerged recently. So people used to understand the beauty of numbers, how these numbers are arranged and how these patterns are made more and more beautiful. In that way also a person can study, and that is what we call aesthetic mathematics. So beauty of numbers is one of such a study. You can see different types of number arrangements. These are all very interesting parts of mathematics. Now, whenever we think about a day-to-day activity, we are in one way or other way involved with a model. Now we have to deal with the one kind of a model or other kind of a model in our day-to-day activities. How we use the types of models. Mainly we have two types of models. That is, one is the deterministic model and the other one is non-deterministic models. The types of models are actually, we chose a type of model depending upon the data which we have. If you are having a specific type of data, we create a model in such a way. Okay, so suppose you know what is actually behind the hidden what is a hidden formula behind a data, then that is a deterministic kind of a model. If you don't know exactly what is happening in that particular situation, in such cases we will say that that is a non-deterministic model. What are the deterministic model? Suppose if you are having a data coming from a deterministic situation, that is, you already know what is the mathematical formula behind such a physical law, then we say that the model is deterministic. Now how we can say that model? We have various deterministic situations in our day-to-day activities. One such model is a differential equation model, as I told you, that you may have a set of assumptions that suppose you consider a bacteria colony over time. That is, the rate of change of the population size may be proportional to the existing or current size of the population. Suppose y is the rate of suppose the rate of change is actually same as the current population, then, or constant times the current population. Suppose the rate of change of the population is constant times the rate of change of the current population, then we can model it in this form, and we are actually getting a differential equation model. So this is a deterministic situation because we already know that rate of change is actually equal to or proportional to the current model, directly proportional to the current population. In that case, the model is dy by dt equal to ky. So this is a deterministic model, and this is, since differentials, the derivatives are involved, we call it as a differential equation model. But in many cases, we may not be able to say that this is the exact principle working behind this. So in such a situation, we may know that some theory is there, some physical law is there, but we cannot exactly recognize what is happening. For example, suppose in the case of a sun, you cannot exactly go and measure the temperature, pressure, or luminosity or the size of the sun, you cannot exactly go there and measure. So how you cannot identify the density of the sun. So in that case, what we can do is we can suggest a model, or we can suggest an algebraic model and say that this will address many parameters which is directly observed from the sun. Suppose we can directly observe the luminosity of the sun. We can directly observe. We can directly measure the pressure or temperature. From different methods, we can measure all these parameters. But the density we cannot measure. So what we can do is we will assume that, or we could speculate that this type of a model will work for the density or the distance of the sun from the center to the from the outer layer. So if you assume f of r equal to a times 1 minus r times a, where a is greater than 0, here as comma is there. So f of r is equal to a times 1 minus r. This is a model which I am simply suggesting. There may be this may be not correct exactly, because many answers we cannot say, many questions related to the sun cannot be answered by using such type of a model. This is a model which I have obtained by using some speculations. Maybe sometimes this is not correct. At some position at some x equal to r by r naught, this is correct. That is why I have assumed this type of a model. But this is not correct. This is a model which I have constructed by using the algebraic technique. So that is why I call this model as an algebraic model. So a more accurate model can be like this: f naught plus 1 minus x raised to delta whole raised to rho. So these type of models is actually what we use in our day-to-day activities is called the algebraic models. But in many situations, in exactly for the sun, we cannot say that these algebraic models are working very well. This may not be the correct model for modeling the sun. So in that situation, what we are going for is the computer models. Suppose we know various parameters related to the sun, and what we do is with the change or change happening in the sun with respect to each parameter, we find a set of equations which satisfies various parameters. We are having a number of differential equations which satisfies these parameters. So we are having a number of differential equations which cannot be solved directly by human calculation. So we use this in the form of a computer model, and we call it as a computer model. Standard models, or that we use for the sun, is what we call solar models. The major drawback of this type of models is that these type of models may not be exact or accurate. In many situations, there may be the error term will be much high. Okay. One of the convincing model which we use in our day-to-day activities is actually the physical the model called power law model. Suppose we consider, as we considered earlier, we may consider a reaction diffusion problem, or we can consider an energy production problem, or we can consider a situation in such a way that a radioactivity problem. In many problems, we can use this power law. Suppose if y is the original amount, and if the decay, if it is in a decay situation, we call the power law model in this form: dy by dt equal to minus a y raised to alpha. This is a non-linear model. Earlier, what I have shown a differential equation model, it is a linear model, but this is a non-linear model where alpha is a non-linear function. So these type of models also we encounter in our day-to-day activities. And another model which is related to this is the input-output model, that, as I have already told you about the production destruction type model, or in business, or as in business, you are having a production based on certain raw materials. Then there is a production model. There is some input called raw material, and the output is the product itself. So that is a model. Or storage of grains in a garden, or melatonin production in a human body, or solar neutrino problems. These are all models which are related to the input-output models. These are all related to mathematics. Now, Another important model is, as I told you, that when we observe nature, we have seen the model called Fibonacci sequence models. Suppose in a growth mechanism, you could see that the new generation, this generation is the resultant of the last two generations. Then in that case, we are coming up with a Fibonacci sequence model. That is, the generation will be in this form: 1, 1, then 2 plus 1, 3, in that way. So this is what we call a Fibonacci sequence model. And in this model, we can predict what is the number of population, or FK denotes the number of population. Then FK, what is the population at the kth generation? This can be done by using the simple techniques of mathematics. And even though mathematics, in model building, the mathematics is not directly involved, we may be simply adding, but in behind it is we are simply using the techniques of linear algebra. So how this FK denotes the population size, how we can identify what is FK, the population at the kth generation. We are having initial condition that F0 is 0 and F1 is 1. These are the initial conditions. And using this model, we have the model that Fk plus 2 is Fk plus 1 plus Fk. This is the model which we call for the Fibonacci sequence model. So how we can find Fk? Fk can be found by simple techniques of this linear algebra. How? We take another equation, Fk plus 1 equal to Fk, and we are having a system of equations like Fk plus 2 equal to Fk plus 1 plus Fk, and Fk plus 1 equal to Fk plus 1. Okay, now you can represent this in the form of a matrix. If you find this in the form of a matrix, you can represent this in the form of a matrix by taking Vk equal to Fk plus 1 and Fk. So actually our model will be like this: Vk plus 1 equal to A times Vk, where A is nothing but the initial conditions. So from A, we can see what is A. A is from this. If Fk plus 1 and Vk is Fk plus 1 and Fk, we can make this in this form. Okay, where A is 1, 1, 1, 0. Now, what is the initial condition V0? V0 is actually F1, F0, which is 1, 0. By using this initial condition, we can actually obtain Vk plus 1. And once we obtain Vk plus 1, we can obtain Fk. So what our aim is to find Fk. Okay. So what we can do is, we have V1 equal to A V0. I hope you can understand this. V0 is 1, 0. Vk plus 1 is A Vk. So V1 is actually A times V0. So V0 we know. V0 V2 is similarly we can say V2 is A V1. In this way, what is Vk? Vk is nothing but A raised to k times V1. So in order to find Vk, we have to find A raised to k. So how we can find A raised to k? That is by using the techniques of eigenvalues. We can compute the eigenvalues of A, and by that we can evaluate Vk. So A raised to k V0, V0 we already know 1, 0 is V0. So we can take the value, we can find the value of A raised to k. So you know what is the relation between A raised to k and A? I think many students may be knowing that the eigenvalues of A and A raised to k will be the same. So by using that technique, we can find the eigenvalues by using the characteristic equation. We know that the characteristic equation is A minus lambda equal to 0, determinant of A minus lambda equal to 0, and these are the two eigenvalues. And many of you may be knowing that these two values are nothing but the golden ratios. So eigenvalues, we can find the eigenvalues of A raised to k are lambda 1 raised to k and lambda 2 raised to k. So the eigenvectors corresponding to lambda 1 and lambda 2 are A minus lambda 1 I of x equal to 0, that is x1 equal to lambda 1, 1. I'm not going to the deeper part of it, calculation part of it. Anyhow, by using this, we are getting with the eigenvalues, and we are getting the matrix of eigenvectors, which is lambda 1, 1, lambda 2, 1. And you can take the inverse, Q inverse, and finally we are getting what is A. A can be written as Q D Q inverse, where D is the matrix formed by the eigenvalues. So by this technique, we can find A, and for finding A raised to K, you simply take the kth power of this. So you are getting this. And finally, we are getting Vk as this. So thus we have obtained Vk, and in our particular situation, we have Fk equal to equation as in equation number 7. Now you could see this Fk can be approximated in the form. So Fk plus 1 by Fk, the ratio of two Fibonacci sequence is nothing but the golden ratio, 1 plus root 5 by 2 or root 5 minus 1 by 2. So these are known as the golden ratios. Now, there are many other models which we usually encounter in our day-to-day activities. One such model is actually the pathway. The pathway model is actually a model introduced by Matai in 2005. This is actually a model from which one can move from a generalized type 1 beta model to a generalized type 2 beta model and to a generalized gamma model. So what is actually the functional form? The three different functional forms used by pathway model. That is, the type 1 beta form of the pathway model is given in equation 8. The type 2 beta form of the pathway model is given in equation 9. And the gamma form of the pathway model is given in equation 10. Now, as you could see that as Q tends to 1, these two models, that is F1 of X, the models given by F1 of X and F2 of X, moves to the model F3. This is the gamma model. In mathematically, these are three different functional forms. But notable thing is that this F1 of X and F2 of X there is no difference, functional difference. There is no much functional difference. Only change is that this minus is taken outside. But the behavior is entirely different for these two models. The first model will depict a cutoff situation, whereas the second model will be depicting the infinite tail case. So, and as this Q tends to 1, these two models will be going to the gamma model. Gamma model is actually the Gaussian model, or what we call the normal model. So this we can see that the type 1 beta model and type 2 beta model are the general cases of this gamma model. Gamma model is the limiting case. So how this is physically used in our day-to-day life? So this is the gamma model. As I told, there is a cutoff in the high energy tail. You could see there is a cutoff. This is the type 1 form of the pathway model. This is the type 2 form of the pathway model. The same situation is actually studied by Salis in his paper in 1988. And this has given birth to a new branch of science called the non-extensive statistical mechanics. The statistical mechanics which we usually study by means of this Shannon entropy or generalization of the Shannon entropies. This is another generalization of the Shannon entropy by generalizing this parameter. That is, that in Salis used to say it as a non-extensive statistical mechanism. So how this type of models are used in our day-to-day activities? Let us see that. So for that, we need, I am not going to explain the special functions at this moment. I will just skip this part and will explain how this model is being used in a real life situation. You know that Sun is the planet which is the star near to our planet, and how the energy generation is taking place in the Sun. That is by particles are colliding in this, that is by using the nuclear fusion reaction. So how this mathematics is involved in this fusion reaction, that we can see. See here, the reaction takes place in the crust and it comes to different zones and finally reaches the sun's, the planet. Okay. Now, how the reaction takes place? Suppose you are having two particles are colliding, you are getting a third particle and a fourth particle with some energy. And this energy is being calculated by using the famous equation of Einstein. So when two particles are colliding with each other, there is a probability is coming that there will be a collision and the energy will be produced. So there is a probability arising out of it. And when the probability is arising, you are getting the reaction rate probability index. So this equation represents, equation 32 represents the reaction rate probability integral in the Maxwell. Suppose you take this is a reaction rate probability integral with f of v as the relative velocity. What are the main particles for a fusion reaction? One is the reaction cross section and the other one is the relative velocity. Whenever two particles are colliding with each other, we are getting a third and fourth particle. So this is actually symbolized here. 1 plus 2 is given as 3 plus 4 plus some energy. That is given equation 31. Now, here the main factors which affects the reaction rate is nothing but the reaction cross section and the relative velocity of the particle. The reaction cross section means the cross section in which the particles are colliding, and the velocity is which the particles are colliding. Suppose you take a unit volume of the sun, and if you consider the reaction taking place in sun, then it is nothing but the average of the reaction cross section with the relative velocity. So this is in statistics, you may be knowing this as the expected value of sigma v. This is the expected value of sigma v. Sigma average angle bracket is used to say that this is an average. So sigma v, average of sigma v, expected value of sigma v is v times fv sigma v d. Now here I have used a non-resonant reaction cross section. In that case, the equation will be in this form. And if you use Maxwell-Boltzmann situation, you are going to use this equation. So if you use these two equations in this equation 32, you are encountering with the value an equation like this. So this is what we call the reaction rate probability integral in the Maxwell-Boltzmann situation. Okay, but in real life situation, in real situation, this Maxwell-Boltzmann, the Maxwell-Boltzmann situation is only when there is a hydrostatic equilibrium. That is, there is a constant temperature, pressure, etc. Then only we can say that the velocity distribution is Maxwell-Boltzmann. But in actual situation, that there is no hydrostatic equilibrium. So we have to think about velocity distribution which are different from the Maxwell-Boltzmann situation. So as I told that I have suggested a model called pathway model. We can use that model to say, see here I have said that this model can be moved from 3 different functional forms. So this is actually the situation of the Maxwell-Boltzmann form or the Gaussian form. These are the non-Gaussian forms. So if you are having a Gaussian form, you can model the non-Gaussian situations. And as limiting the q tends to 1, you are actually getting the Gaussian situation. So this can be exactly used here in our physical situation and can be obtained to extend the reaction rate probability. So that is what we have done here. You could see that here, this instead of using this Maxwell-Boltzmann velocity distribution, we can use the pathway energy distribution. This is an energy distribution defined by myself, and this energy distribution can be used instead of this Maxwell-Boltzmann, and we can extend this reaction rate probability integral in the Maxwell-Boltzmann case. And how this energy density is used here? This is by taking the cutoff case, by considering by the single equation, we can consider the cutoff situation as well as the heavy tail distribution. Both we can consider by using this particular equation. That is the advantage of this model used in this extended reaction rate probability. So anyhow, thus we can obtain a generalization of this in real life situation. Okay, so this is what I wanted to mention to you. I just don't want to go further into this because this involves a theory of mathematics, or those which may be not followed by the layman, or those who are not familiar with mathematics may be not happy with this. So this is what I wanted to point out, that Mathematics is a subject which is being used in many places. Only problem is that many people are not aware where they are using it indirectly. So many places mathematics is being used indirectly. So once we identify the application of mathematics or working of mathematics, we could see that this nature is actually governed by mathematics. So for the younger community, I would like to say that you observe nature or the natural aspects, because nature always works simple or simple by using the simple techniques in mathematics. Once you observe nature or the natural techniques in a simple way, we can develop big theories, or we can explore more mysteries in our universe. So with this, I would like to stop because it's already 1 hour. I am sorry for taking more time uh, because this content had to be like that. So anyhow, thank you very much for your patient listening, and I sincerely thank Professor Ahmed Ali and Babu Banarsi Das University for giving me an opportunity to deliver a talk. Thank you very much, sir. And I would be happy to answer a few questions. By the way, let me say that as I told that there is a determinist situation, there are non-determinist situation models also. So as where there is a, if in determinist situation, we know already what is happening, but there are situations we don't know actually what is happening. In that case, we call it as random. So or random situation or non-deterministic situation. So random walk models are non-deterministic situation, branching process models are non-deterministic, or birth death process time series models or regression type models. All these are non-deterministic models. So all these are directly or indirectly involving mathematics. So that is what I would like to say. So Amdali sir.
So thank you, Professor Dilip, for this wonderful talk. I think you touched so many areas and really showed the importance of mathematics and rather appearance of the mathematics in a very natural way in many areas such as nature and etc. So thank you very much. And if anybody has a question, you can raise your hands. Any question? So if there is no question, then let's thank speaker once again. And Professor Dilip, on the behalf of Department of Mathematics and Computer Science of Babu Banarsi Das University, and on my personal behalf, I express my sincere thanks for this wonderful talk. And I'm sure that there are young boys and girls who are exposed to a lot of applications they might have not thought of even or may not be aware of. And this will be maybe a point of starting point, and they must be motivated, and they will take the exploration further of the applications of mathematics and its importance. And that was the very purpose of this talk also. So thank you once again, Professor Dilip, and thanks everyone for joining this session. And I hope that we will have a more association with Dr. Dilip, and our department will be benefited in future also. So thank you, Dr. Dilip. Thank you very much.
Thank you, sir. Thank you very much for giving this opportunity. I think that I don't know whether the talk has been useful or I thought